Okay, here we go. And you can see some of my scratch that's left here from our last lecture where we started talking about hybridization, and I explained a little bit about what orbital hybridization is. And if you weren't there, or if you're wondering what I'm talking about, is if you think about um, s orbitals. So you know that an s orbital is a sphere, right? If we have an s, it's a sphere. And if you have a p orbital, it kind of looks like a dumbbell. Okay, there's no orientation of s orbitals or p orbitals that would explain where we get a tetrahedral molecular geometry, right? If you have, the p orbitals, something like this, okay, and then another p orbital in the back here, there's no way that you would explain the 4 points of the tetrahedron. Another thing that we're going to look at, and this won't be today, this will be probably on Wednesday, is we're going to discuss why oxygen is attracted to a magnet. And that's what's being shown here in this figure. This comes straight out of the textbook. This is liquid oxygen that's in here between two magnets. And if you look at the Lewis structure that we drew for oxygen, and if you were to draw that as a Lewis structure for oxygen, I would give you one. I'd give you the double check mark. I'd say pat you on the back. You're great, But it doesn't explain why oxygen is attracted to a magnet, does it? Because in order for something to be attracted to a magnet, it's got to be paramagnetic, and so that means it's got to have an unpaired electron. It looks to me like all the electrons in this Lewis structure are paired up. Okay, and that's kind of the purpose behind this whole chapter. I'd say the first part here, this is going to be today's lecture, and then this part here, we're going to discuss that on Wednesday's lecture. Okay, let's get a couple things out of the way here about what's called valence bond theory. So we're talking about the bonding between atoms to form molecules, and they're bonding using their valence electrons. That's what valence bond theory means. Now, the basic principle of valence bond theory says that a covalent bond forms when we have orbitals that overlap. Okay, we've looked at all kinds of orbitals, s orbitals, p orbitals, d orbitals. Those orbitals are going to overlap, and a pair of electrons is going to occupy the overlap region. Okay, what's a pair? A pair means two. Okay, that's why in a bond we have two electrons, because a bond is the result of orbitals overlapping. And as it says here in the first point, when orbitals from atoms overlap, we have a pair of electrons in that overlap region. Let's move on. The space formed by the overlapping orbitals can accommodate a maximum of two electrons, and these electrons have to have opposite spins. Okay, so one's going to be spin up, and the other one's going to spin down. Again, so what's going on is we have two orbitals overlapping, and when those two electrons are in that orbital, that overlap, one's going to spin in one direction, the other one's going to spin in the opposite direction. Here's another cool one. The greater the orbital overlap, right, the more efficient the overlap, the stronger the bond is going to be. Right, think about it. The whole concept of bonding is the result of overlap of orbitals. So the more overlap we have, stands to reason that the stronger bond we should get. And lastly, the extent of orbital overlap is going to depend on orbital shape and direction. And that's something that we'll look at a little more as we progress on through the chapter. So let me just erase some of this scratch and we'll keep moving here. Here are some examples of orbital orientation and the maximum overlap that we can get from these orbitals. Let's start out by looking at two s orbitals. So two 1s orbitals. I don't mean a 2s, I mean a 1s, but two 1s orbitals, okay? Think about hydrogen. What's the electron configuration of hydrogen, right? We have a hydrogen, it's 1s1. We have another hydrogen, it's 1s1. That's what's being shown here. We have two spheres, okay? They're both labeled as 1s. They even put the letter H in there to remind you that it's a hydrogen, and they get the two electrons. Now, those two spheres come together, right? And we get this overlapping of the two spheres. You see the overlap region here? It's a little bit darker, right? That's the overlap region. And you can see the two spheres can overlap quite efficiently. And we have the two electrons in there, and they're in opposite spin. Here's the Lewis structure of hydrogen shown on the right. Now, what if we have hydrogen and fluorine? What's the electron configuration of hydrogen? Well, we just looked at it. We know that hydrogen is 1s1, and we know that fluorine, and we'll just look at the valence electrons, okay, is, because we're talking about valence bond theory, is 2s2, 2p5. So the 2s2 would have 1, 2, so 2s2, and then we have 1, 2, 3, so 2p, we have 1, 2, 3, 4, 5. So that means that you've got one p orbital that has only one electron in it, right? You've got, did I write 1s2 for hydrogen? Mr. Dion, you've had too much wine. Okay, there we go. Anyhow, so we've got 1s1 for hydrogen. And then for the fluorine, what I'm getting at is that you have one p orbital that's got one electron in it. What's that electron want to do? What does that electron in that p orbital want to do? It wants to overlap to form a bond, right? And that's what's happening here. So, and if you're like, well, come on, Mr. Dion, aren't there 3 p orbitals? Here I only see 1. They've left out the other 2. Okay, so they're not showing the 2 other p orbitals. It's been left out on purpose. They're highlighting in the book that you have a p orbital, okay? There, it's the dumbbell, and that's the 1 p orbital that had only 1 electron in it. And then they're showing it overlapping with a 1s orbital. And here's the region of orbital overlap. Where's my red pen? Yeah, here's the region of orbital overlap. Okay, and there's the Lewis structure of HF shown on the right. What's another, orbital orientation? Okay, so far we've looked at 2 s orbitals. They come together head on. An s orbital will always combine with a p orbital in this orientation. Okay, where sort of the, I don't know what you'd call this lobe of the p orbital will, overlap with the sphere of the 1s. And if we have two p orbitals, and I don't mean a 2p orbital, I just mean 2 different p orbitals. They could be 3p, they could be 2p, they could be 4p. But anyhow, if we have 2 p orbitals coming together, the most efficient way that they can overlap is what's shown here. Okay, so I've already shown you the electron configuration of fluorine, and we said that we have 1 p orbital that is missing an electron. So those 2 p orbitals are going to come together. We call this head-to-head. Okay, or at least that's what this guy calls it. I call this head-to-head overlap, like that. And that is the most efficient way that they can overlap. Let me talk to you guys and show you my face here for a second. Okay, you're like, no, not the face. Okay, anyhow, here's a p orbital. Okay, this is my dumbbell. This is my arm. Like, here's one lobe, here's the other lobe. Okay, I'll need to back up here, won't I? Okay, the most efficient overlap that you can get between 2 p orbitals is when they overlap like head to head like this. Now, this is what I wanted to tell you, is that somebody might be thinking, well, what if the 2 orbitals come and they overlap like side to side like that? Wouldn't that result in an overlap? And if you're really just like, Mr. Dion, what are you talking about? Let me show you what I mean. Okay, and this is something that we're going to look at in a second. I just like to always kind of help my students put a bug in their ear before we get to something. So what I'm getting at is this. This is head-to-head overlap. There's somebody out there in the class who might be wondering, well, what if I had 2 p orbitals and they overlapped kind of like side to side like this? Okay, this is side to side. And you might look at this side to side overlap and you might think, hey, man, that looks like even more overlap. You got overlap here, you got overlap here. Hey, that's even better. That's more efficient. It's actually not. Okay, it is not the most efficient. Okay, so what's the title of this slide? Orbital orientation and maximum overlap. Head to head is max. That's the maximum overlap. When they're side to side like this, it's not the maximum overlap. And that actually forms a different kind of bond, and it's a weaker bond. Okay, and I will get into that in even more detail later on in the class. Let's get back to some theory that I want you to know before we keep moving on. The orbitals that form when bonding occurs are different from the atomic orbitals in the isolated atoms. Okay, so we're going to be looking at a whole bunch of new orbitals today. If no change occurred, we could not account for the molecular shapes that are observed. If you're wondering what it's saying here in this bullet point, all she's saying is, if all we had at our disposal were s orbitals, spheres, p orbitals, dumbbells, the d orbitals and the f orbitals, we would not be able to rationalize things like a trigonal bipyramid, a tetrahedron. Okay, we wouldn't be able to do that. So what we're going to see is that we're going to take the orbitals that we know, s orbitals, p orbitals, d orbitals. We're not going to be looking at f orbitals whatsoever. and we're going to mix them together, and we're going to form what are called hybrid orbitals. The spatial orientations of these new hybrid orbitals that we're going to look at are going to correspond with the observed molecular shapes that we learned in chapter 10. The tetrahedron, the trigonal bipyramid, the bent shape, the trigonal, the octahedron, so on and so forth. Anyhow, you know what the shapes are. Okay, what else do we need to know? The number of hybrid orbitals, and if you're wondering what a hybrid orbital is, trust me, we're going to look at a lot of them. The number of hybrid orbitals formed equals the number of atomic orbitals that are mixed. Okay, so if we mix 2 orbitals that are atomic orbitals, we're going to get 2 hybrid orbitals. If we mix 3 atomic orbitals, we're going to get 3 hybrid orbitals. So if we mix 6 atomic orbitals, we're going to get 6 hybrid orbitals, so on and so forth. The type of hybrid orbital formed varies with the types of atomic orbitals that we mix. So the types of hybrids that we're going to get are going to depend. Are we mixing an S and a P, an S and 2 Ps? Are we going to put a D in there? What are we mixing? Okay, and then the shape and the orientation of a hybrid orbital maximizes the overlap with the other atom in the bond. Let's start with the first example of a hybrid orbital. Now, in order for us to understand the hybrid orbital, I want to back up a little bit because we spent a lot of time in this class already talking about Lewis structures. Do you remember we looked at the structure of this guy right here, BeCl2, beryllium chloride? Well, hopefully you remember that beryllium is an exceptional atom in that it doesn't need to have a full octet of electrons. In fact, it can only form 2 bonds. That's something that we discussed earlier on in this class. And so I'm not going to reteach the Lewis structure for beryllium chloride, but the Lewis structure is this. We've got BeCl2, 2 bonds from the beryllium to each chlorine atom. Okay, we've got 2 bonds. Now, we've got 2 regions of electron density around the beryllium, right? 2 reds. So it's going to adopt a linear molecular geometry, 80 degrees, and it's linear. Now I want to back up to another chapter and talk about the electron configuration in BeCl2. What's the electron configuration? And again, we're only talking about valence electrons, so I'm going to forget about the 1s2. I mean, you can write it in if you want, but let me just write it. We got 1s2, 2s2. These are the valence electrons. Here's the box diagram shown here. I've got 2s2. Both of those electrons are paired up in an s orbital. How in the heck can you form 2 bonds if you've got 2 paired electrons? You've got to have an unpaired electron. Okay, you've got to have unpaired electrons to make a bond. If I have 2 bonds, that means I'm going to need to have 2 unpaired electrons. Okay, so here's what we do, is we take one of those electrons, it doesn't matter which one you put a circle around, okay, and we're going to move it up into a 2p, and then we're going to mix the orbitals. What are we mixing? We're mixing 1 2s orbital and 1 2p orbital. So if you mix 1s and 1p, you get what's called an sp. Now you've got 2 sp orbitals, and they each have 1 unpaired electron in them. Okay? The other 2p orbitals, those are unhybridized. Don't worry about them. Okay? They are unhybridized orbitals. Are they still there? Yes. But their shape isn't changed. They're still the same old dumbbells, and they don't have any electrons in them. Now, if you're not following me 100%, let's go over it again, but we're going to look at it in terms of a picture. If I have my beryllium atom, I have 2 s orbitals, and I have 2p orbitals, okay? Here's the shape of an s orbital. It's a sphere. Here's the shape of a 2p orbital, okay? This is the dumbbell shape, okay? This is what Mr. Dion would draw like this, but this is how Dr. Silverberg does it when she's got a fancy computer. What you're going to do is you're going to take those 2 orbitals, you're going to put them in a blender and mix them up, okay? It even makes that sound. I'm kidding, but... And then you form what's called an sp orbital. You see how the sp orbital, since it was made of a big old 2s orbital and the 2p orbital, you kind of get this like big lobe, and then you've got the little lobe here. Well, those two sp orbitals are going to overlap like this, okay? And then it says the linear orientation of the sp hybrid orbitals. So this shows the overlap of the two hybrid orbitals. Now, the simplified view is what I'm going to be using all of the time, okay, is the simplified view. And in fact, this little part over here, we're just going to leave that out, okay? So what I would usually draw is something that looks like this. So, and instead of, letting my students be confused, I will just write the name of the hybrid orbital. So I would write sp like this, and then I've got an sp like this, okay? So I've got two hybrid orbitals. They're both sp orbitals, and they both have one electron in them. So this is what I would draw, is I would put one electron here and one electron here. Are the p orbitals still there? Can anybody tell me, are the other 2p, the unhybridized 2p orbitals, are they still there? It's not a trick question, just a yes or a no. Does anybody know? I've said it earlier. Aaron says yes, and he's absolutely correct, okay? Yes, they are. Look, the other 2p orbitals, the unhybridized orbitals, you'll have one like this. This is a 2p orbital, and the other one is, like this, okay? This is a 2p orbital. They're there, but we leave them out, generally speaking, okay? We just leave them out, so I don't draw them. Other little nuances that I want to point out to you guys, like things that, sometimes irritate students, are this. So I'm sure there's somebody in the class who's thinking, well, come on, Mr. Dion, you mixed a 2s, that was the principal quantum number, 2, and you mixed a 2p. Why are you just calling it an sp? Why don't you call it a 2sp and a 2sp? That's just a convention. We usually leave the principal quantum number out when we describe a hybrid orbital. I know it's irritating to some people, but that's just the way we do it, okay? If you go on the internet, it'll do it that way. If you look in another chemistry textbook, it'll do it that way. Okay? All right. Give me a thumbs up if you follow me thus far. That in order for beryllium to make those two bonds, we had to put an electron into a 2p orbital, stick them in a blender. You took one s orbital and one p, so you made sp. It's 50% s, 50% p. And now you've got two new hybrid orbitals, right? These are the hybrid orbitals. These are the hybrid orbitals, and they each have one electron. Okay? Remember, this is just a model that we use to explain the linear geometry of BeCl2. Okay, now there are quantum mechanical calculations that support this, that support orbital hybridization. But we're using this hybridization to help us understand or rationalize why BeCl2 or why beryllium forms two bonds, and it has that linear geometry. That's why we had to look at that first. Now, let's look at the Lewis structure in more detail. Here again is a picture showing the 2s of our beryllium. Okay, this is just showing the valence electrons of the beryllium right here. We've got two electrons in here, like this. We've got three empty p orbitals. Then what we do is we move one of those electrons into the p orbital. We stick them in a blender, and we end up with this, the two different sp orbitals. So this is an sp orbital, and this is an sp orbital. Again, when Mr. Dion is drawing these in front of you guys, he's going to leave out this little nub, this little lobe here, okay? Now let's think about BeCl2 some more. You've got BeCl2. Okay, put in all my lone pairs here. Now we've got the beryllium, right? This is the sp orbital. This is an sp orbital. These are the 2p. I told you that they're usually left out. Here they are in our beautiful textbook. Now chlorine, I'm just going to write up here. What are the valence electrons of chlorine? You got 3s, 3, come on, Mr. Dion, 3, letter S, 2, 3p, 5, okay? So you've got S, you've got your 3s, and then you've got 3p, 1, 2, 3, 1, 2, 3, 4, 5. So this is 3p. So you've got one p orbital that has one unpaired electron. Are the other 3p orbitals there? Yes, they're just left out, okay? She just leaves them out because it's just easier to just look at that. Then we have the maximum orbital overlap. So the head of this unhybridized chlorine 2p orbital that has an unpaired electron, this guy right here, it's going to overlap with the hybrid sp orbital, and there you go. There's the region of orbital overlap. There's two electrons. They have opposite spins, and there you go. Give me a thumbs up if you follow me on this. Okay, even if you're 50% of the way, even 40% of the way, we'll do it for now, because we're going to look at several examples before we're going to go home, okay? You know, it ain't over, okay? It ain't over yet. We got a lot of ground left to cover. There's a lot of hockey left to play here, so to speak. Okay, look, I know I keep harping on the same pictures, but this picture is so great. You look at this beryllium right here. You've got two regions of electron density explained by our hybrid orbitals. They're going to want to get 180 degrees apart from each other, and that explains the linear geometry. Okay, so hybrid orbitals. Okay, so that explains why BeCl2 is linear. Explains why beryllium forms two bonds. Let's look at another example. Let's look at boron trifluoride. I'm going to go a little faster here, not too fast, but a little faster. And you know that the Lewis structure of BF3, boron trifluoride, is this. You've got boron. Boron is another exception. It only forms three bonds. It doesn't need a complete octet. Okay, boron forms three bonds like this to the fluorine. If we look at the electron configuration of boron, okay, 1s2, 2s2, 2p1. Let's concentrate on the valence electrons only. Remember, this discussion is about valence bond theory. So valence electrons. We've got a 2s, okay, and we've got 2p. There's three types of p orbitals. We've got two electrons in here, and we've got one in the p. That's what's drawn here too. Okay, I've just drawn it horizontally instead of vertically. Now, if you look at the electron configuration of boron, it's got one stinking unpaired electron. Where does it go off making three bonds? It can't. It's got to have three unpaired electrons in order to make three bonds, just like beryllium needed two unpaired electrons to make two bonds. What are we going to do, people? We're going to take one of these tasty, tasty electrons, and we're going to move it up into a 2p orbital. Okay? And then you end up with sp2 orbitals. That's the name of the new hybrid orbital. Why is it called an sp2? Because it's made from one s, son of a gun. It's made from one s orbital and two p orbitals, right? If you look at it horizontally, okay, you end up with this. You have 1, 2, 3 orbitals. They're called sp2. You're going to have 1, 2, 3 electrons, okay? And then you still have the 2p, and there's nothing in it. It's unhybridized, okay? Remember, what's in the gray box? That's what you're hybridizing. What does hybridize mean? What's a hybrid car? A hybrid car is one that's not an electric car. A hybrid car runs on electricity or gas, depending on the situation. So we're mixing s orbitals and p orbitals. Now we can see that if we make three hybrid orbitals, right, they're going to want to maximize their distance. So I'm going to draw one here. So we'll call this an sp2 orbital. We'll call this an sp2 orbital. Again, I'm trying my best here, people, to draw. Okay, we'll call that an sp2 orbital. Okay, and if you're thinking, that looks an awful lot like your sp orbital, Mr. Dion, you're darn right it does. Okay, it's the best I can do. All right, how many unpaired electrons are there in each of these sp2 orbitals? There's one here, there's one here, and there's one here. Why does the boron in boron trifluoride adopt a trigonal planar arrangement? Because you've got three regions of electron density. You've got those three sp2 orbitals, and they want to maximize the distance between each other, and so they're going to have bond angles of 120 degrees. Now, what about fluorine? Okay, fluorine is 1s2, 2s2, 2p5. So if we think about the valence electrons, you've got 2s. Sorry, my Apple Pencil is like misbehaving here. 2s with 1, 2. You get 1, 2, 3, 2 p's. 1, 2, 3, 4, 5. So it's got a p orbital. with one unpaired electron. What's a p orbital look like? Right? A p orbital looks like this, and it's got an unpaired electron. So that means they're going to overlap head to head like this. So this is a fluorine, okay? And it's going to have an electron with opposite spin, right? Because each fluorine is going to bring one electron to the table. Now you've got another one here. That's another fluorine. Maybe I'll put fluorine in them like that. It's going to have an electron with opposite spin. And then you're going to have another p orbital from the third fluorine. Okay, and it's going to overlap like that. You want a prettier version of it? Okay, fine. Okay, here you go. Here's the drawing made by Dr. Silverberg. Yeah, sure, it's prettier than mine. Okay, but where did that unhybridized 2p orbital go? It didn't go anywhere. It's still there, right? It just doesn't have any electrons in it. So there's my unhybridized 2p orbital. Remember, this is a model that we use to explain why boron trifluoride is trigonal planar. Give me a thumbs up if that helps, what I just did. All right. You know what? Okay, I only got one thumb up. Okay, oof, tough crowd. All right, well, let's look at some more. We're not done. Let's look at some more. What about methane? What's the electron configuration of carbon? Okay, these are things you should be able to do quickly by now. 1s2, 2s2, 2p2. If I draw the orbitals, I have a 2s. It's got 1, 2 electrons. I got 1, 2, 3 types of 2p orbitals. You have 1, 2 electrons. Carbon forms 4 bonds in methane, right? We should have something that looks like this, CH4. I'm drawing the VSEPR structure. It's the tetrahedron, like that. So that means that carbon has to form 4 bonds. That means I have to take one of these electrons, move it up here. And when you do that, you're going to end up with this. Now you're going to have 1s and 3 p's all mixed together. So you're going to call it sp3. It's 25% s and it's 75% p. Now you've got 1, 2, 3, 4 electrons. They're in 4 different hybrid orbitals. Okay, each hybrid orbital is the same, but there's 4 different ones. Okay, 4 different orbitals. Anyhow, so you're going to start with drawing your carbon. Okay, I'm going to erase this. Think about it. If I have 4 hybrid orbitals, they're each sp3, right? This is an sp3, son of a gun. Right, this is an sp3 orbital. This is an sp3. This is an sp3. This is an sp3. If I have 4 of anything, how are they going to get as far away from each other as possible? You're going to have one sp3 orbital going like this with an unpaired electron. You're going to have one coming down like this. That's an sp3 with an unpaired electron. I'm going to draw one in the back. I'll just draw it with a dash like this. That's an sp3 with an unpaired electron. And then I'm going to have one coming out in the front. I'll try to draw it kind of shaded here. It's coming straight for us, okay? And it's going to look like that. So when you draw methane, hydrogen does not have to hybridize. Hydrogen only has the 1s1. And so all those spheres all overlap with the end. So you would literally draw a sphere on the end of each of these, right? And then you have an electron coming from hydrogen in each of these, and that shows the orbital overlap. Give me a thumbs up if that helps. The sp3 orbital. Or if you're with me on the sp3 orbital. Okay, this is why you have to understand Lewis structures and VSEPR theory in order to get this far in the class, right? If you still can't draw a Lewis structure, I would get it why this wouldn't make any sense. Okay, so I'll slow down again just for a second here. If you think about NH3, ammonia, nitrogen has 5 valence electrons. Hydrogen has 1 valence electrons. There's 3 of those. So we add that up, we get 8 valence electrons. We start drawing a Lewis structure. Hydrogen can only have 1 bond. We've only used up 6 electrons. We have 2 left. So the nitrogen has 4 regions of electron density. So that means that, and I'm going to erase this, that if we have 4 regions of electron density, that ammonia is going to look something like this, where we'll have a lone pair up here, we'll have a hydrogen going in the back, and we'll have another hydrogen coming down here like this. Could anybody tell me what, how do I delete that? What the molecular geometry of ammonia is? Not a trick question. We've looked at it many times. Trigonal bipyramidal, absolutely. So trigonal bipyramidal, okay? Sorry, no, it's not trigonal bipyramidal. It's trigonal pyramidal. Anyhow, so trigonal pyramidal. Sorry about that. All right. Anyhow, so trigonal pyramidal. If we look at the orbitals, okay, the valence electrons, we've got a 2s. It's got 2 electrons. We've got a 1, 2, 3. We've got 2p orbitals. We've got 1, 2, 3 electrons. Okay, things that you need to know is that there's only one kind of s orbital. There's 3 types of p orbitals. How many types of d orbitals are there? How many types of d orbitals are there? There's one kind of s orbital. It's just a sphere. There's 3 kinds of p orbitals, px, py, pz. How many types of d orbitals are there? Where do we find d orbitals? Where's the d block on the periodic table? Right? There are 5, thank you. There's 5 types of d orbitals. Okay? So, if you look at this, you might think, hey, this is perfect. I've got a lone pair here, and then I've got 1, 2, 3 unpaired electrons. But the problem is that would not explain the trigonal pyramidal shape. It wouldn't explain how these 4 regions of electron density get as far away from each other as possible. Okay? If we want them to get as far away from each other as possible, we're going to have to hybridize all 4 of those orbitals, okay, to give us 1, 2, 3, 4 orbitals, and we'll call them sp3. Except now we've got 1, 2, 3, 4, 5. Now that explains why we have a lone pair and we've got 3 bonds. Okay, so we've got 3 sp3 orbitals. Let's look at oxygen in water. Okay, if we look at the electron configuration of oxygen, we got 1s2, 2s2, 2p, 4. If you look at the valence electrons, I'm just doing the same thing over and over. 2s, 1, 2, 3, 2p's. We've got 1, 2, 1, 2, 3, 4. You might look at this and it might be your knee-jerk reaction to say, hey, the oxygen in water, okay, has 2 bonds and it's got 2 lone pairs. You've got one, maybe I should draw it the way she has it here just to make it easier. Okay, so she drew it like this. She's got her oxygen. She's got a hydrogen coming over here, another one coming out like this. She's got a lone pair in the back, and then she's got a lone pair up front. So maybe I should draw this on a wedge like that. That's kind of how she drew, right? So you can see the bond angle here, which is bent. Okay. Anyhow, it might be a knee-jerk reaction to say, hey, look, 2 lone pairs and 2 bonds. I'm good. No, because that wouldn't explain why those 2 lone pairs and those 2 bonds are spread apart as far as possible. It wouldn't explain why the electron geometry is tetrahedral. And so we have to mix all of those orbitals. We have 1s and we've got 3p, so we call it sp3. But now we've got 6 electrons. 1, 2, 3, 4, 5, 6. Now it explains why we've got 2 lone pairs and 2 bonds, like that. Okay? Give me a thumbs up if you follow me on that, or if it's helping. Or you could even stop me if you have a question, which I'd be happy to address.
Okay, stupid question. No, but the S, like the P3, that's because you have 3 of like 2 P's, right?
Exactly.
Okay.
Yeah.
Okay. Thanks.
So the fact there's no superscript next to the 1, next to the S, means that there's only one of those. And the fact that this superscript here is number 3 is that there's 3 p orbitals, right? 1, 2, 3. Okay? And that you used all 3 of them. You have no unhybridized orbitals on the oxygen and water. Okay, well with that, I'm going to skip this slide here because I put that in the wrong spot, and we're going to look at phosphorus pentachloride. Let me just pause here for a second and put a plug for our textbook. If you go to section 11.1 in our textbook, there's a video in there that explains everything that I'm covering right now, and it takes 10 minutes, and it is very, very well done. Okay, it is done with animation, so it shows all the orbitals coming together. I would recommend taking a half an hour and watching that 3 times, because you will definitely understand it at the end of that. Anyhow, let's look at phosphorus pentachloride. By now, you should know that phosphorus pentachloride is a trigonal bipyramidal shape in terms of its molecular geometry. I'll draw it out here. We got one chlorine in the back like this, another chlorine coming out in front like this, okay? The question we want to ask ourselves is, how do we rationalize phosphorus having 5 regions of electron density, right? How does it have, look, 1, 2, 3, 4, 5 regions of electron density. And beyond that, why are they spread out as far as possible to make this trigonal bipyramid, right? We want to answer both of those questions. Trigonal bipyramidal. Why? Why did that happen? In order for us to understand that, we've got to back up and we've got to look at the valence electrons of phosphorus, because valence electrons are the electrons that are involved in bonding. If we look at phosphorus, phosphorus is element number 15 on the periodic table. The noble gas that precedes it is neon. What comes after neon? We've got 3s2 and 3p3. Now, all this work is done right here, but I'm just going to draw it out here. If we draw 3s, there's only one type of s orbital. It's got 2 electrons in it. How many types of p orbitals are there? There are 1, 2, 3. We'll call them 3p. And there are what? 3 electrons in there. 1, 2, 3. Remember Hund's rule, right? The bus rule. Okay. This does not explain how the phosphorus could have 5 regions of electron density. In order for the phosphorus to form 1, 2, 3, 4, 5 bonds, it's got to have 5 unpaired electrons. I can't simply take this s orbital and put it into a p orbital. I've got a problem then too, because I'd still have paired up electrons. Okay, so what I have to do then is I have to access the d orbitals. Remember that when you go from 4s2, you go to 3d. So elements in the 3rd period and beyond have d orbitals available to them. Okay, that's why elements in the 3rd period and beyond can expand their octet. And so you guys just told me there's 5 types of d orbitals. I don't know if I have enough room, but 1, 2, 3, 4, 5. All right, 3d here. And so what I'm going to do is I'm going to promote that electron all the way into a 3d orbital. Then what am I doing? I'm mixing 1 s orbital. Sorry, I'm trying to draw good here. I've got 1 s orbital. I've got 1, 2, 3 p orbitals, and I took a d orbital. I stuck all of them in a blender, and now I've got sp3 d orbitals. That's the name of this new hybrid orbital. And I've got 1, 2, 3, 4, 5 electrons, 1 in each of the sp3d orbitals. And I'm going to have 1, 2, 3, 4 3d orbitals left over with nothing in them. Okay, they're unhybridized. So I start by drawing my phosphorus. Now it's kind of hard to see here, but it's got 1. This is an sp3d orbital. 2. This is an sp3 d orbital. You can see there's one in the back here. That's another one. This is another one. And then this is one. All 5 of those sp3 d orbitals want to maximize their distance. So they adopt a trigonal bipyramidal shape. Now, chlorine, we already discussed why chlorine doesn't have to hybridize. It's got an unpaired electron in a p orbital. And so she left out the other 2 p orbitals. Yes, they're here, right? They're in there. She left them out because it would look like too busy. But the hybrid orbital from the phosphorus, the sp3d orbital, is going to overlap with the unhybridized p orbital from chlorine to get maximum orbital overlap. And in each one of these regions of orbital overlap, there's going to be 2 electrons with opposite spin. She hasn't included them just because she realizes that if you get, if you draw everything in, they get kind of hairy, kind of hard to see what's going on. Give me a thumbs up if you're improving in your understanding, because we have one last one to look at. No, maybe we get a couple actually. Yeah, I picked 2 more examples. Okay, let's look at another molecule then. Let's look at chlorine trifluoride. Let's think about chlorine trifluoride for a second. Am I on the wrong page here? Messed up. Oh, probably. Doesn't matter. Anyhow, how many valence electrons are there in ClF3? How many valence electrons? Not a trick question. This is something we should be able to do in 1 second. How many valence electrons in ClF3? This molecule is made up of 4 halogens. They all have 7 valence electrons. 7 times 4 is 28. Good. So we've got 28 valence electrons. Okay. Fluorine can only ever have 1 bond. Okay. Like that. In 3 lone pairs. I've used up 24 electrons. That means I'm going to have 25, 26, 27, 28. And so the molecular geometry of chlorine trifluoride will be T-shaped. Okay, that's the molecular geometry. The electron geometry is trigonal bipyramidal. Okay, but the molecular geometry is T-shaped. How do we explain this electron geometry? This trigonal bipyramidal, trigonal bipyramidal electron geometry with 2 lone pairs. If we look at the electron configuration of chlorine, okay, it's neon. Then we've got 3s2, 3s2, and we've got 3p. Son of a gun, I got the number 2 on the brain here. 3p, 5, 1, 2, 3, 4, 5. That means that it's got 1 unpaired electron. How in the hell could it form 3 bonds? We're going to have to promote some electrons into the orbitals. Let's do that. If we take 1, 2, 3, 4, 5, 3 d orbitals, and if we move one of those electrons, okay, one of those paired electrons into a d orbital like this, and then if we have 1s, son of a gun, it's really hard for me to draw straight at the bottom of the slide. 1s, 3p, in a d orbital, and I've got 1, 2, 3, 4, 5, 6, 7 electrons. 1, 2, 4, 5, 6, 7 electrons. I've still got sp3 d orbitals. I've got 1, 2, 3, 4 unhybridized 3 d orbitals. But that explains the 5 regions of electron density around my chlorine, and it explains why I have 2 lone pairs and 1, 2, 3 bonds. All right. Let's look at one more example. And this is sulfur hexafluoride. Sulfur hexafluoride is octahedral. I'm not going to reteach the molecular geometry. I'll just draw it out here. It's octahedral. Okay, you should have been practicing this all weekend so that you can nail it on a Monday. Maximize your investment. How do we rationalize that sulfur has 6 regions of electron density? When we look at the electron geometry of sulfur, it's simply 3s2, 3p, 4. Here's our 3s, 1, 2. Here's our 3p. It's got 1, 2, 3, 4. In order for it to form 6 bonds, 1, 2, 3, 4, 5, we have to take our 3d orbitals, and we're going to have to promote 2 electrons. We'll take one of them and put it into a d, and another one and put it into a d. Then we'd have something new. We'd have 6 hybrid orbitals. 1 from the s, 3 from the p, and 1, 2 from the d. So we have sp3d2. And each one of those is going to have 1 unpaired electron. And that explains why we have 6 bonds, 6 regions of electron density that are spread out as far as possible in the octahedron to give us an octahedral electron geometry and molecular geometry. Okay? The summary of everything that we've just looked at is right here on this page. If you mix 1s and 1p, I'm right here, okay, then you're going to form 2 hybrid orbitals. They're going to be sp orbitals. You're going to have 2 unhybridized orbitals. They're going to be p orbitals, and it's going to be linear. Okay. If you have 1s and 2p, you're going to have sp3 orbitals, 3 regions of electron density, 1p orbital that's unhybridized, you're trigonal planar. If you have 1s and 3p, you're going to have sp3. Okay. You're going to have no unhybridized orbitals, and you have tetrahedral molecular geometry, so on and so forth. Okay, so that is valence bond theory. I didn't mean to close down my whole slideshow. That was a mistake. So with that in mind, let's back up here. Okay, hybridization patterns. 2 regions of electron density. Your hybrid orbitals will be sp. If you've got 3, it's sp2. 4, it's sp3. 5, it's sp3d. 6, it's sp3d. Okay, and these are the percentages. Of course, if you have 1s and 2 p's, well, it's 33% s, 66% p. If you get sp3d, it's 20% s, 66% p, so on and so forth. Fingers. Look, I'll show you how. Didn't mean to do that. Meant to do that. Look, you can just do it like this. You go sp2, so sp, okay, so that's 2 bonds or 2 regions of electron density. sp3, or sorry, sp, sorry, get 2 regions of electron density. sp2, 3 regions of electron density. sp23, 4 regions of electron density. sp23d, so that's sp3d, it's 5, and sp3d2 is 6 regions of electron density. Anyhow, there you go. Don't say I didn't give you anything. Joel, let me ask you something. Would you have to memorize the percentages? Is that necessary? What do you think? If I told you you have an if I told you had sp3, you know it's made out of 1s and 3 p's. Do you really need to memorize that? If you take 100 and you divide it by 4, each one of these is 25%, right? So on and so forth. And if there's 1s and 3 p's, so Joel, you don't have to memorize it, but you have to know it. Okay, I would say memorization not required. Okay, just some quick math. All right. From molecular formula to hybrid orbitals. This is all the cool things that you've learned. Okay, all the neato things that you've learned in the past, I don't know, few weeks, I guess, of your life. Molecular formulas. You need to learn how to draw Lewis structures. Then you learned VSEPR theory. You learned how to draw molecular shapes. And then finally, you learned about hybrid orbitals. And so that's why I warned you about this many times throughout this, the past few weeks. I said, you got to understand this part to get to this part. You got to understand this part to get to that part, so on and so forth. So if you're the kind of person who, it takes you a lot of time to understand the concepts in chemistry and to really master them, you got to be relentless. You got to be like a pit bull and just to go after it and keep going, and, just be really relentless on the weekends and on your evenings and practice. It is really the best way to master this material. Okay, well, with this in mind, let's move on and look at something that's interesting here. It says use partial orbital diagrams to describe how mixing of atomic orbitals of the central atoms leads to hybrid orbitals in each of the following: methanol and sulfur tetrafluoride. Jeepers. Maybe we can start with sulfur tetrafluoride. That might even be easier. Okay, let's start with SF4. I think it's probably simpler in some ways. So how many valence electrons are there in SF4? We got 6 plus 28. Okay, I'm going a little faster now. We got 34 valence electrons. Sulfur, we have 1, 2, 3, 4. I'm just doing this quick and dirty here. My Lewis structure, I've used up 8 times 4, which is 32. I've got 2 left. There we go, 34. So I've got 5 regions of electron density. 5 regions of electron density. I'm going to erase all this. This is just I'm hanging out at Dairy Queen and, writing on the back of a napkin. So now that I know that it's 5 regions of electron density, I can make it look a lot prettier because I know it's going to have a trigonal bipyramidal electron geometry. Could anybody name the molecular geometry for this guy? Could anybody name the molecular geometry for this guy? If I take a trigonal bipyramid and I remove one atom from the equatorial position and I replace it with a lone pair, what's this called? Yeah, thanks, Aaron. It's the seesaw. Seesaw, not seesaw. Good gravy, man. Okay. Anyhow, so how do we explain? So this is what we're gonna do. We're gonna show how we mix atomic orbitals to have 5 regions of electron density, and one of them is a lone pair, and 4 of them are bonds. So that means we're going to need 5 hybrid orbitals. One of them is going to have a lone pair, and then one of them is, or 4 of them are going to have single bonds. Now, if you're thinking, well, come on, if I've got 5 regions of electron density, you already told me the last slide. You summarized it, Mr. Dion. You gave away the answer, right? We already said if you've got 5 regions of electron, it's going to be sp3d. We know that. Okay, you're right. I know. I know the answer. I just want to work it out as a group. Okay, so we know it's going to be sp3d. Let's see if we can come up with a rationale. I think we can. Sulfur. We got neon followed by 3s2, 3p4. We got the 3s. We got 2 electrons. We get the 3p. 3p. 1, 2, 3, 4, like that. This does not explain 5 regions of electron density where we have 3 unpaired electrons and a lone pair. But if I access the 3d orbitals, and if I move one of these stinking electrons into here, that arrow isn't very pretty, is it? Into here, okay, then I'll mix them, hybridize, okay. Then I'll end up with this, an S, 1, 2, 3 P's, and a D. So I've got sp3d. I'm going to have 1, 2, 3, 4, 5, 6 electrons, like that. Okay, I've got a lone pair, and I've got 3 unpaired electrons to make bonds. Where are my other 3d orbitals? I'm the teacher. I'm not going to leave them out. You've got 4 unhybridized 3d orbitals. Okay, so these are, let's just go over this again. I hate it when I just get into the exciting part and then my iPad decides to be a big J-E-R-K. Over here we spell that word because we don't want our kids to learn it. So these are hybrid orbitals, and these are unhybridized. Okay, unhybridized. I'll shorten it there. Okay, so there we have it. So that means we've got sp3d hybridization. Give me a thumbs up if that helps. You're like, I'm killing it. Just watch me, as Pierre Trudeau would have said, or as he did say. All right. Who wants to try something a little more challenging? Let's try a molecule where we have 2 central atoms. All right, great. This is good. I hope this is helping you guys. Again, let me put in a plug for our textbook. I don't do that a lot, okay? I mean, I like the textbook and all, but I find like she spends a lot of time talking about other stuff sometimes. If you go into section 11.1, okay, section 11.1, and there's a video in there, and it is awesome. Anywho, let me show you this quickly. We'll go over the hybridization of the central atoms. Remember, we're looking at central atoms here for methanol. We already looked at the Lewis structure of methanol, so I'll just help you here. We got this. Based off of everything I've taught you today, you should already know the hybridization of the carbon is sp3. It's got 4 regions of electron density. The hybridization of this oxygen is sp3. It's got 4 regions of electron density. Let's start with the carbon. Okay, looking at just the valence electrons, I'll just do a little quicker here. We got 2s2, 2p, 2. Okay, we're gonna hybridize those into 1, 2, 3, 4. So now we've got sp3 orbitals. We're gonna have 1, 2, 3, 4 unpaired electrons. That's how we form the 1, 2, 3, 4 bonds around the carbon. For oxygen, again, looking at the valence electrons, 2s, there's 2 electrons in there, and then the 2p, there's a total of 1, 2, 3, 4. We're going to hybridize those into 1, 2, 3, 4 sp3 orbitals. We're going to have 1, 2, 3, 4, 5, 6, because we need to have 2 bonds and 2 lone pairs. All right, we got 2 bonds and 2 lone pairs around this oxygen. And so that explains the hybridization of the oxygen. That's it. Here are the solutions. We'll skip these pop-up questions for now. In the last 2 hours of lecture today, I want to go over types of covalent bonds. And the reason why I skipped those pop-up questions is we'll come back to those later when we have time. But I wanted to cover this because I kind of already put the bug in your ear earlier today. So I think it's important we take a look at this. A sigma, so sigma, this is the Greek letter sigma, bond is formed by end-to-end overlap of orbitals. All single bonds are sigmas. The 3 types of sigma bonds that we look at in this class are either if you have 2s, if you have 2 s orbitals, okay, if you have an s and an s orbital overlapping like that, if you have an s and a p, so here's a p orbital with an unpaired electron, here's an s orbital, they're over. So if you have an s and a p, or if you have 2 p's, let me do my best here. You have 2 dumbbells overlapping, comme ça, as we say in French. There we go. So those are all sigma bonds. The pi bond, that's the one that's formed by the side-to-side overlap. That's the one I was trying to show you with my arms, okay? When you have p orbitals, okay, that are overlapping side-to-side like this, it might be a knee-jerk reaction, like I said, to say there's 2 kind of spots where it's overlapping. This side-to-side orbital overlap is actually weaker, okay? It says here it's less effective, okay? So it's weaker than a sigma bond. A double bond consists of 1 sigma bond and 1 pi bond. A triple bond consists of 1 sigma bond and 2 pi bonds. Let me show you what that means, okay? And that, to put that another way, would be like this. Any bond after a sigma bond is a pi bond. If you have, I don't know, let's say you have fluorine, okay, F2, the bond, right? This bond is a sigma bond. If you have oxygen, let's say, like this, the first bond is a sigma bond. Anything after a sigma bond is considered a pi bond. Okay, and if you're like, does the sigma have to be on the bottom like that? No, I could have drawn it from the top. It doesn't matter. Let's say you have nitrogen, N2, like this. Okay, the first bond is a sigma. Both of these, okay, that's a pi bond and that's a pi bond. Okay, if you had CO2, okay, if you had CO2 between two atoms, the first bond is sigma. This is a sigma. Anything after a sigma is a pi. This is a pi. If you had this molecule, acetylene, C, right? This is called acetylene. It's used for welding. Anything, you know, this is a sigma. This is a sigma. This is a sigma. Anything after a sigma, this and this, those are both pi bonds. Do you read me on sigma and pi bonds, my friends? Okay. So now that we've cleared up what a sigma bond is and what a pi bond is, let's look at the bonds in the ethane molecule. It says here the sigma bond is formed by end to end overlap of orbitals. Okay, so I'm making a ethane molecule for you right now. Just give me uno segundo here, and I'll make an ethane. It says the sigma bond has its highest electron density along the axis, shaped like an ellipse. Okay, like a football. Yeah, let me show you my model. I'll do that in a second, actually, because then we're going to look at ethylene. And the pi bond is formed from the side-to-side overlap of orbitals. The pi bond has two regions or lobes, one above and one below the plane. And what that does is it causes the molecule to not be able to rotate. Let me show you on my thingamajig here. Stop that. Can you see me now? Can everybody see my model? My model? Okay. It's my best Newfoundland impression. Okay. Cha-cha-cha. Here's the model of ethane, CH3, CH3. These are all the bonds in here are sigma bonds. There's free rotation around a sigma bond. You see me spinning it there? I'm not going to break anything. I'm not going to ruin anything. Nobody's going to call my parents. Okay. Okay, there we go. That's a sigma bond. If I remove the sigma bond, and if I make the ethylene molecule that has a double bond, to make a double bond with these, you use these longer links. You see how it's quite a bit longer? And then you bend them, okay? And then I'm going to make a pi bond, okay? The first link represents a sigma. The next one represents a pi. But look, so it's CH2, CH2. There's no free rotation. Do not rotate, okay? We'll break models. We'll be in big trouble, okay? So that's an ethylene molecule. And if I make a triple bond, whoa, Nelly, okay? Close your eyes, okay? Let's see here. If I make a triple bond, so take another one and bend it again. There you go. There's a triple bond. So this is acetylene, CH-CH, and you can see that there definitely isn't free rotation here. That's good teaching. All right. Students need sound effects in their lives. Where the heck were my students? Start broadcast. Oh, share screen. Can you see my screen again?
Yep.
Okay, great. Thanks, you guys. I appreciate that. So again, in ethane, all the bonds are sigma bonds. So say here, all sigma bonds. Then when you get to ethylene, right? This is a sigma, this is a sigma, this is a sigma, this is a sigma. These are all sigmas, but this one down here, okay, that's a pi bond, okay, and it is caused by the orbital overlap side to side. So you get side to side, okay. Mr. Dion, when he draws it, it looks like this. It's like crap, but hey, they don't hire me because I'm a great artist, okay. That's the best I can do, you guys. I'm sure you can all draw it better than me, okay. But what really happens is they overlap like this, okay? Now, here's a trap that I've seen a student fall into a couple of times, not often. But if you show them this orbital overlap like this, every once in a while, I'll have a student who will say, and don't draw this, okay? Do not draw what I'm drawing, okay? It would be a big no-no. They'll say, well, there's a lobe here, so that's a bond. And then there's a lobe down here, so that, whoa, hold the phone. Oxygen can't exceed enough. Let's delete that. Ooh, oh. We're in some kind of super high energy state there. It didn't feel right. Okay. This whole kit and caboodle here, this whole thing, that's one bond. I know it looks like you get a spot here and a spot here, like, hey, there's two bonds. No. That is one bond. Please give me a thumbs up if you understand that when the two p orbitals overlap side to side, that's one line in your Lewis structure. And that is the pi bond. Don't ever. Okay, good. All right. Okay. I don't know if I've ever told you guys this before, but I know I've told you many times, probably Avogadro's number of times, that I spent most of my adult life working as an organic chemist, and carbon can only ever have 4 bonds. I mean, if we were interviewing people with PhDs and master's degrees, and if anybody ever tried to draw a 5th bond to carbon like that, we called it the Texas carbon. Anyhow, that's more what they call it down here in the States. But if anybody ever drew a bond, an extra bond to carbon, I mean, we would just go back to the office, take their CV, and just like file it in a circular can called the trash. They were like, where did this person get their degree? Did they find it in the used clothing store? Okay. Anyhow, a little comedy for you there, but sad but true, right? Anyhow, we looked at the orbital overlap in acetylene. I showed you the model, and I explained why these are all sigmas, and then, sorry, did I draw 2 bonds to sigma? Mr. Dion is getting tired. Okay, there we go. And then if we draw these, so anything after a sigma, these are pi's, okay? So the triple bond consists of 1 sigma and 2 pi's. You can hitch your wagon to that. That's for every triple bond you'll ever see for the rest of your life. Okay, no exceptions to that rule. This is just a relief map showing electron density and bond order and ethylene, and acetylene. Something I should have pointed out maybe or mentioned on the fly was that when you have a single bond, that's got a bond order of 1. If you've got 2, it's a bond order of 2. If you've got 3, it's a bond order of 3. And the double bond is twice as strong as a single. The double bond is less than twice as strong as a single. Why? Because a pi bond is weaker. Okay. And all they're showing here, you guys, all you need to understand is that the more orbital overlap you have, the more electron density there's going to be between the 2 atoms. Nothing more than that, just for you to understand what the heck is going on. You know what? Let me add one more fun thing to this point right here before I move on. If I have, you know what? We got 3 more hours. So if I draw an acetylene molecule, an ethene molecule, okay, this is ethylene. You can call it ethene as well. Both are correct. If one of those bonds is a pi, okay, let me highlight it. If one of these is a pi and one is a sigma, let me ask you an honest question. Which one do you think is going to react first, the pi bond or the sigma? And it's not a trick. It's an honest question. Which one do you think would react first? If you were to throw HCl on this, hydrochloric acid, Aaron says the pi bond, and he's right. Right? Camden says the same thing. The reason why is not meant to be anything complicated at all. The pi bond is weaker. If something is weaker, thank you, Isabel. Exactly. The pi, if it's weaker, it's going to react faster. That's it. A sigma bond is more stable. And so when you guys get into organic chemistry, because you're all going to take it with me, right? Wink, wink, okay? When you do, We'll talk all about pi bonds, and we'll discuss even all the different types of reactions that you can do with a pi bond. Really enjoyable. Anyhow, where was I? Oh, I want to show you this too, the restricted rotation around a pi bond. How many minutes do we have? 86 minutes. Can I just show you one that I think you would find enjoyable? Where's my ethane molecule? Just give me 1 second. Oops, didn't mean to do that. Where's my camera? Where am I? Here I am. I just want to show you something quickly here. It would be better if I had two models. Let me find another chlorine atom here. Anyhow, look, I'll do my best to ask you all a question here. Okay. So this, here's a molecule. Okay. Look at it carefully. If carbon with a double bond, this is a chlorine, this is a chlorine, this is a hydrogen, this is a hydrogen. If I swap these two, okay, if I swap those two, is this the same molecule that I just showed you? Yes or no? Is this the same molecule or a different molecule? Okay, it's different, right? Because before the chlorine was on the same side of the molecule as that chlorine. And remember, there's no rotation around a pi bond, so I can't rotate this to get that one back up there. If I did, I'd break the model. The only way is to literally break those bonds. And so those two molecules where you have the chlorines both like this, or if I had put the chlorine down there, those are two different molecules. Different melting points, different boiling points, different dipole moments. Interesting stuff, huh? Anyhow, it's 10:40. I should probably call it a day.